introduce the first speakers. Professor Jie Shan from Cornell University, and she's talking about the magnetic 2D materials and its magnetic restrictions. Okay, please.
Thank you. Thank you very much. And so I first would like to thank the organizers for inviting me. You know, I'm not a MEMS person. You know, we are just learning the system, trying to you know, using MEMS technique to study some physical properties, 2D materials. So this really is an honor to share with you some of our recent studies of 2D magnetic materials and learn what's going on in this field. Before I start, I would like to acknowledge my collaborators, Professor Kim Van Mack, who co-supervised the group with me, and also the real heroes, you know, the postdocs and the students who have made this study possible. So mainly postdoc Shenwei Jiang and two former students, Hong Chao and Zhe Fang, and a current student, Li Zhong. Okay. So controlling magnetic states in materials is not just fundamentally important, but also technologically very important, including information technology, you know, magnetic actuation, transduction, sensing, and other applications. And we can control the spin of electron or some other particles by coupling through charge or some spin mechanical coupling or coupling to light. And this, of course, is not a new topic. Research has been done like for many years. So mostly in bulk materials and other thin film magnetic materials. And what's relatively new in this field is the recent discovery of atomically thin magnetic materials. So here are a couple of papers from 2017. So for example, this team from UC Berkeley and UC Irvine reported that chromium, germanium tellurides it persists to be a ferromagnetic in relatively thin thickness. And in this joint study of Washington and MIT, they showed that a chromium iodide is ferromagnetic down to monolayer limit. So what's remarkable about, you know, those new discoveries is that now we have two-dimensional crystal material, which will allow fundamental study of magnetism in the true 2D limit. And the atomic thickness of these materials allows very efficient control of their magnetic states by electrical means, you know, like you can put them into sort of capacitor-like structure, and you can apply large field or using electrostatic technique to introduce large doping density. And the high mechanical stiffness and the strength and the low mass of these materials are ideal for, you know, magneto-restrictive phenomena and applications. So I hope I'll be able to give you some example, you know, along those lines. And it turns out that there is a very large class of crystalline layered materials that are magnetic. So I'm just listing a few here, and the schematic in the bottom just shows the magnetic ordering. So the spins are, those blue balls, they are in honeycomb structure mostly. And the white and the black are spin orientation in opposite direction. And it could be out of plane, so perpendicular to the sheets, or in plane. So you can have a wide range of magnetic orders, antiferromagnetic zigzag, stripy, or neo, or some A-type of antiferromagnetic, so one layer along one direction, another layer along a different direction. So today I'm going to focus on one particular crystal, which is chromium iodide. So this is, okay. So this is sheets of a crystal looks like this. The white balls are for the magnetic atoms, the chromium, and the blue balls, the iodine. And this is in hexagonal structure in this edge sharing octahedral coordination. So each of them will have 6 iodine atoms. And the magnetic atom has 6 electrons, and it donates 3 to the iodine atom, and we have 3 left. The crystal field splits the levels, such that you have T2G and EG level, and the 3 electrons just sits in the T2G, and they all aligned. And the material has very strong spin-orbit coupling, which is in the outer plane direction. So the spins are aligned, either up or down. So effectively, you can think of this as like a close to 2-dimensional Ising magnet. It has been a lot of studies on the bulk material in terms of synthesis and characterization. So we know that the Curie temperature of this material is around 60 Kelvin, and we can exfoliate it down to monolayer thickness. And this is a kind of a magnetic circular dichroism measurement. So what we are doing is to look at the absorption difference between the left circular polarized light and the right circular polarized light. So you can think of magnetic circular dichroism in this limit sort of proportional to magnetization. Okay. So what we are showing here is magnetization as function of outer plane magnetic field. So in a monolayer, it's a ferromagnet. So zero field, you already have non-zero magnetization. And then when you increase the field, you can switch the direction of the spin orientation from down to up. And what's surprising is that when you have 2 sheets of those materials at zero field, you actually get a 0 magnetization. And if you apply something around a half Tesla, then suddenly you turn on a large magnetization. So and then when you reverse the field direction, you got a hysteresis and then go to the other direction. So this tells us that bilayer actually is an antiferromagnet, and those are 2 possible spin alignments in the 2 layers. And this is something what people refer to as A-type antiferromagnet. So 2 different layers, antiferromagnetic coupled ferromagnetic layers. Okay. So why the magnetism, in the bulk, it's a ferromagnetic coupling between the layers, and then in very thin layers, it's antiferromagnetic coupling is an interesting topic by itself. So the key ingredient is exchange interaction is very sensitive to the stacking order between the layers. So that's kind of a difference. And I'm not going to talk about this. So let's just agree on the experimental fact that in field layer chromium iodide, we have antiferromagnetic interaction as ground state. So let's just take a look at the energy scales involved. Okay, so we saw that the Curie temperature is on the order of 60 Kelvin, and in terms of energy, that's around 4 millieV. So that tells us that the interlayer magnetic interaction is on the order of 4 millieV. And then in the bilayer experiment, we saw that we need to apply a field on the order of a half Tesla to flip the spin and make antiferromagnetic to ferromagnetic spin flip transition. And this half Tesla corresponds to energy of, on the order of 0.1 millieV. And this corresponds to the interlayer magnetic exchange. So now we have two very different interaction energy scale, and this interlayer magnetic interaction is relatively weak. So this gives us a window to control the interlayer magnetic interaction while keeping each layer still ferromagnetic. So now, after this short introduction comes to my outline. So in this talk, I would like to discuss briefly, how to control the interlayer antiferromagnetic or ferromagnetic interaction using electrical means. And then hopefully, I will go to mechanical technique to control that. And I think this is the main interest of this conference. So first, I would like to discuss the possibility of using a pure electrical field to control the magnetic states. And this is sort of very important for technology because, you can tune if you can tune the magnetic states without involving current, you can reduce the energy consumption of this operation significantly. So to control magnetic states using electric field in the linear order, we know this is something called the linear magneto-electric effect. You can write down the free energy of the system in the presence of external electrical field and a magnetic field, assuming the system has a permanent electrical dipole and a magnetic dipole. So in the leading order, you can write down the coupling between magnetic field and electric field just by this linear term alpha times E field and the magnetic field. And by performing differentiation, with respect to field, then we can get a polarization or magnetization. So in order for this alpha to be non-zero, then the system has to have broken inversion symmetry because, under inversion, the polarization goes to negative and the magnetization doesn't change sign. So for this to be non-zero, we have to break inversion symmetry. And by very similar argument, for this to be non-zero, we also need to break a time reversal symmetry because, under time reversal operation, magnetization changes sign, but electric field doesn't. So just from this basic symmetry analysis, we know if you want to get relatively large or non-zero, at least linear magneto-electric effect, the material has to have broken both inversion and time reversal symmetry. So we are dealing with those ferromagnetic or antiferromagnetic materials, so we don't need to worry about time reversal symmetry. It's broken. How about inversion symmetry? So let's just take a look at the structure in a monolayer limit. So if you don't consider spin here, the structure, atomic structure itself has inversion symmetry. So I can just put my point here. You can go from this to that. So structure-wise, it has inversion symmetry. And in the monolayer limit, when you do inversion, spin down goes to spin down. So ferromagnetic, this monolayer has inversion symmetry. So now if we go to 2 layers, the structure itself is still has center of inversion. So, I can put my point here. You can find symmetry between the top and the bottom layer. However, if we include all the spins, as I mentioned, under inversion, spin doesn't change. Therefore, if the 2 layers are both ferromagnetic, we have inversion symmetric structure. However, in antiferromagnetic bilayer, inversion symmetry is broken. So just from this kind of simple symmetry argument, we know that we only expect to see non-linear magneto-electric effect in bilayer antiferromagnet. So just for a sanity check, we study monolayer first. So we put this between 2 gates and then apply a perpendicular electrical field. And we apply already a huge field, on the order of 0.5 volt per nanometer. And as you can see, the MH curve of monolayer barely changes. So this, no obvious magneto-electric effect, linear magneto-electric effect. So, and this is consistent with our symmetry argument. So now let's look at the bilayer. So in the absence of electrical fields, we have seen earlier that, zero magnetization at 0 fields. And when you increase the magnetic field, you switch the spin. It's a spin flip transition, and it's a first order transition. So we have magnetic hysteresis, and that's expected. And now if we increase the field perpendicular to the layer, now suddenly the magnetization is no longer 0. And if you keep increasing the field, and the magnetization increases. So if you just keep track of what's going on as a function of electrical field, the red line, at the 0 field increases linearly, and the black line also increases in terms of magnitude, with field. And if you park somewhere here in the ferromagnetic state, we see negligible magnetization change here and there. And this is also expected from the symmetry analysis, right? Because, this state, ferromagnetic bilayer, has inversion symmetry. So we expect a linear magneto-electric effect to go to 0. And you see a little bit of effect, and this is, it depends on field non-linearly, and that doesn't violate symmetry argument. So And looks like, using electric field, you can turn on magnetization somehow. The microscopic mechanism of this effect is still under study, and we think, so this could be an explanation, is that, when you apply electrical fields, the two layers are at different potential, and you can induce a charge transfer from one layer to another. And because of the strong interlayer magnetic interaction, the spin transferred to that layer will have to line up with the rest. And then if you are in this situation, the net magnetization will be up. So that's how we can get those non-zero magnetization when you apply field. And this also gives us, a hint that if you can introduce doping into the system, perhaps you can do this more efficiently. And that's what we tried in the next experiment. So now we put the structure in kind of a two-gate geometry, and somewhere here, because this chromium iodide itself is very insulating, and here, if you apply, gate voltage here and there, you almost don't dope it because, charge cannot flow into it. But if you look at, the area sort of overlapping with graphene, so you can have charge flow into graphene and graphene jump into chromium iodide. So like this overlapped area can be heavily doped because chromium iodide has very flat band, so it can hold a lot of charge. So let's just take a look, at the doping effect. And again, this is the same measurement, magnetization as a function of outer plane field. This is the case when we don't have any doping, and you can see that the two layers already develop some magnetization. And the reason is because the top layer and the bottom layer are not symmetric. One is in touch with graphene, the top and the bottom is in touch with HBN. And now if you apply a large voltage, so then you put in a lot of charge carriers into chromium iodide, and you can see that, this antiferromagnetic range becomes smaller and smaller, and at a sufficiently large doping density, we can almost, make the transition from antiferromagnetic to a ferromagnet. And this is extracted interlayer exchange energy as a function of gate. And you can see that, at large gate voltage, which corresponds to a very heavy doping, it switches sign. So in this convention, we use positive for antiferromagnetic interaction and a negative for ferromagnetic interaction. So, so this is like we can almost turn an antiferromagnet now into a ferromagnet just using electric, using gating. So now, if you think about this, if I apply some constant bias magnetic field, let's say we sit somewhere here, and now you can change the gate voltage. So basically, if we are at this gate voltage, the magnetic state is ferromagnetic. And if you go to somewhere here, it's antiferromagnetic. So basically, we can achieve electrical gate tuning of switching of the magnetic state. And based on this idea, we've demonstrated, spin field effect transistor just using this mechanism. So anyhow, let me switch gear here, talk about using mechanical means to control or detect the magnetic state. So the question we would like to answer is, for example, in this bilayer, in the case of spin antiparallel or parallel, does lattice change? Do you develop a string for those two different states? And if that's true, if we can detect the mechanical property, then that would be a way to also probe the magnetic states. And if this effect exists, then the inverse effect should also be there. So the question is, can we tune antiferromagnetic to ferromagnetic transition by string or some mechanical means? And the experiment was done using this drumhead device. So the radius is on the order of 2 to 3 micron because we want to get to relatively high frequency. And this is the membrane, 2D materials. We put on top of the drumhead, the trenches with electrodes, and the silicon serves as backgate. So you can apply a large gate voltage here just to pull down the membrane. So this is the way to apply continuous string on the magnetic field and at low temperature. So this membrane, of course, the main constituent is the chromium iodide layers. So in this case, I'm showing 2 layers. And one kind of a not very nice property of this particular material is that it's very air sensitive, so we need to protect it. So we wrap it between 2 different materials. One is field layer graphene sheet, usually 1 layer or 2 layer. And graphene is also conducting, so it serves the purpose as just as electrodes as well. And then on top, we put in a monolayer of semiconductor, tungsten selenide. And this serves, not just as a protection layer, and it's also a string sensor. So it has a very strong interaction with light, and optical response of this typically is like a very strong exciton resonance. So this is, taken from this device. If you look at absorption, and this is a large dip, corresponds to the fundamental exciton in this material. If you apply gate, apply string, you see a systematic shift of the exciton resonance. And this is in a relatively small range of string. Exciton resonance shift scales linearly with string. And this is, we can pre-calibrate this, and this serves as a string gauge. So we can independently measure the string level, assuming the 2 layers do not slip. And at the same time, we measure the mechanical resonance and also the magnetic properties using magnetic circular dichroism, as I showed you earlier. And this is our schematic. So, so this is our drumhead device. We use optics interferometric technique to measure the vibration modes, the outer plane vibration of the membrane. So use fast photodetector to capture the reflected light, and then use network analyzer to look at the spectrum. And we, we can apply gate voltage, which is a DC voltage. And on top of that, we put a RF voltage. And this, when we sweep the frequency of the IF, we can sort of capture the resonance. So this is just an example. It's for a bilayer device. And we can see that the amplitude of vibration is a function of IF frequency. And you see a kind of a nice peak here. So the frequency is on the order of 20, 25 megahertz. And the width here is about 10 kilohertz. So the Q of this device is a few thousand. And this quality factor can be further improved if we do a better job, to clamp the membranes. So in this measurement, we just didn't do any clamping. So and then the bottom figure just shows the resonant frequency as a function of the gate voltage. And this pretty much looks like any other drumhead devices made of other 2D materials, graphene or molysulfide, the semiconductors. We have built-in stress, and that determines the frequency at 0 gate. And at a high gate voltage, the frequency scales as a fourth power very quickly. And it can be described reasonably well using the continuum model for tension the membrane, and that's the red solid line. And we neglect the bending stiffness, and we assume there is no slippery at the boundary, so fix the boundary. So you can extract stress, density, Young's modulus, those device parameters, using this model. But to reduce the number of parameters, we can use our gauge I mentioned to you just a few minutes ago, to determine the stress. So to reduce the number of unknown parameters. So by looking at this, we can get Young's modulus, density of mass density. Okay, so now let's take a look at the interaction coupling between spin and the mechanical properties. So now we are going to turn on outer plane field. And we know that if the field is large enough, we will induce the spin flip transition. And what I'm showing here is the mechanical resonance as a function of magnetic field change from 1 Tesla to negative 1 Tesla, and then sweep it back to 1 Tesla. And as you can see here, that the resonance frequency has a jump around the half Tesla. And this figure captures the resonance frequency. And the width actually doesn't change too much. And also, within this range between 0.5 Tesla and the negative 0.5 Tesla, amplitude or width, basically don't change. And the only change is this sudden redshift in the resonance frequency around the 0.5 Tesla. So mechanical resonance is perfectly correlated with the magnetic state, as you can see from those two pictures, And again, this is due to hysteresis, that's first order transition, and that's expected. And the redshift is on the order of less than 0.1% in terms of frequency. But the Q is, large enough, allow us to see this very clearly. The other thing I want to point out is that, so the MH curve, we have negative and a positive magnetization. In the magnetic resonance frequency, we don't see any difference. I should finish, is that right? Hello?
Yeah. Yeah. Already over. So yeah.
Oh, okay.
Could
so,
you?
Sorry, you should have.
Yeah, it's okay,
let me just quickly scan through this.
Okay.
Yeah.
Okay, please.
And so you can test this, with all layer, and again, it's not sensitive to the direction magnetization. So as long as the net magnetization up is fixed, whether it's up and down, the mechanical resonance is not sensitive to that. And the technique is also sensitive to more complex magnetic states in multi-layer samples. And we understand this effect well, and because, in this case, we have a competition between elastic energy and interlayer exchange. And the balance between the two will tell us the built-in stress for two different magnetic states. And that gives us a difference in the mechanical vibration frequency. So this is very well understood. And for multi-layers, the effect is bigger because you have a larger exchange interaction because you have more layers. So anyway, I should wrap up, and it's also sensitive to spin canting if you apply in-plane magnetic field. And unfortunately, I don't have time to discuss this. The reverse effect also exists. So in other words, if you apply strain, you can change the spin flip transition field. So although the effect is relatively small, but it's there. So you can think of experiment like, if I apply a constant magnetic field sitting somewhere here, and then I change the strain by just applying the backgate. I can go from, so in this case, from ferromagnetic to anti-ferromagnetic, and so this can be tuned. So anyway, I used more than what I should have. So let me just put up my summary and I'll finish here. I'm sorry, I lost track of time.
That's okay, yeah. Okay, thank you very much. Now we have 2 questions. So first, by the Kani Mohammed. So can you ask the questions? Hello?
So there is one question in the Q&A. Should I try to read it?
Yeah. So maybe it's better to start from that.
Yeah. So it says, you show that the resonance frequency of the drum does not jump, but also shows values in between the two states. Do you know what happens there? Okay. So I'm not completely sure that I understood the question. So I think if you can speak, you can correct me. So I think what you are asking is the following. Let's look at the 2-layer case. So basically here, the frequency doesn't change and the frequency jumps when we go from, this antiferromagnetic to ferromagnetic spin alignment. And, it has hysteresis, and the transition may not be sort of sharp enough if there's, small domains, here and there. So if this is what you are asking, so this often due to different domains.
Okay. So, Yaroslav.
Right. Thank you for
Okay.
this talk. Very, very interesting. Thanks a lot. I have a question about temperature for the mechanical part in particular.
Mhm.
I guess you are measuring at some fixed temperature.
Yes. So we are all the data I show you is around 3 Kelvin, 4 Kelvin.
Do you have any data which you didn't show, which show any temperature depend?
Oh yes, I don't have it here, and we've done temperature dependence measurement, and so it has a neo temperature, right? So above around
Yep.
yeah, and this goes away, and of course the Q goes becomes a little bit worse, and this is a very good, interesting question. So this is something else we have been studying. Whether using this platform will be able to extract, heat capacitance, the thermal phase transition. So that kind of information. And the short answer is yes. You can look at temperature dependence and do those measurements carefully, and you can learn quite a lot.
Right. My colleagues, experimental colleagues in Delft, actually also see.
Yes. Are you talking about a paper published in Nature Com?
Yeah, exactly. I'm also on the paper. Yes.
Okay. Yeah, I had a
great.
pleasure reading your paper.
Okay, great. So we probably have a lot to discuss. Yeah. Thanks.
Yes.
Thank you.
Okay. So, are there any questions? So I have one question. So you use the bilayer, yeah? So how you can fabricate that bilayer, and how you can control the stacking between these two?
Oh, okay. So we actually don't purposely control the stacking order of the materials. So the way we fabricated those devices is first we exfoliate them on a silicon substrate. So this is just a Scotch tape, and this is a quite random process. Somewhere you get a 1 layer, somewhere you get 2 layers, somewhere you get a 3 layer. So after you do this, and we do optical spectroscopy, so we can identify where we have a 2 layer sample or 1 layer sample, and then we come in and pick up those samples. So in terms of the stacking order, we believe that it's when you do the pressing and picking up, you can perturb the original alignment between the layer, the stacking order, and you can apply a pressure or some other annealing, some other means afterwards to go to the kind of the equilibrium, the lowest energy state, and we've done that, and we've also done experiments, just by making a monolayer and then tear the monolayer into 2 pieces and put on top of the other one with a controlled twisting angle, so you can look at this effect specifically and actually, sort of a different experiment to verify that the stacking order actually changes the magnetic interaction between the layers.
Okay. Thank you. Okay, this is the last questions given by the Andre. Thank you for a nice talk. It's a Q factor of these structures sensitive to antiferromagnetic and ferromagnetic transitions.
Okay. Yeah, so the Q factor actually is not very sensitive to the transition, as you can see from the data. So the width, the width of a resonance basically doesn't change. And then the frequency shifts by a tiny amount. So I'm talking about, 0.1% change in the frequency.
Okay. Okay, this is the final question. So by Ignacio Wilson Lai. So thank you very much for the stimulating talk. You mentioned that changing the clamping is important to improve the Q, but your continuous model, a continuum model, which matches perfectly, assume the perfectly fixed boundary condition. Could you clarify?
Yeah, so that model, we just explained the resonance frequency, and so my statement is sort of based on what other groups have done, and they have seen better Q than ours. So that's why I made the statement that you can improve Q. So I have to say that this continuum model, there are quite a few free parameters, in this model. So it's perfect, almost perfect, but it's not, like if you look at it somewhere here, it's a good fit, but it doesn't mean it's perfect.
Okay, thanks. Oh yeah, Adrian, you also have a question?
Yeah, hi. So I have a question. So you say that you change the strain in the monolayer,
Yeah.
and so it's an elongation along the monolayer axis. But then you speak about a change of the exchange interaction, so which is related to the overlap of the wave function between the bottom and top layers. So it's not very intuitive for me.
Oh, okay. So so we're talking about the in-plane strain, okay, in the drumhead. And so the one thing I probably should have mentioned that the DFT calculations have shown that the ferromagnetic and antiferromagnetic have different lattice constant. So the antiferromagnetic state has a smaller lattice constant than the ferromagnetic state. So that's just from the DFTs. And our result is consistent with that. So the interlayer exchange interaction, actually this is a very complicated process. It could be the bond length, which is the distance between the atoms, and there's also the bond angle between them. So if we only consider, let's say, the bond length change, and so in this system, the exchange is quite complicated. We have chromium atoms and also interaction between chromium iodine, and they have different terms like a nearest neighbor, next nearest neighbor. So some will have positive sign and some have a negative sign. So the antiferromagnetic interlayer interaction is the combination of all those factors. So when you change the layer separation, many terms can change. And from this measurement, we saw that applying string weakens antiferromagnetic interaction. Does this make sense to you?
Yeah, so if the experiment says yes, it makes sense. It's complicated. Thank you.
Okay. Thank you very much for the excellent talk. So let's move on to the next talk. Okay, thank you very much. Okay, so please let me introduce next speakers, Edward Lai from Lancaster University, and he's talking about